Gas stoichiometry. When we look at different reactions, we find that there are a number of different chemical reactions that produce gases. There are also several different types of chemical reactions in terms of classification which produce gases as well. Combustion reactions will consume oxygen gas and oftentimes other gases and produce gases. But more importantly, we can look at things like solution state and solid state chemistry with the production of gases from things like solids, liquids, and aqueous solutions, where we have things such as metathesis reactions of acid-base reactions producing gas sometimes. We have displacement reactions, like reactions of acids with metals that can produce gas. We have decomposition reactions that can produce gas, combination reactions that can produce gas. All of these are possibilities. When we look at gas properties, we know that the molar volume of a gas at standard temperature pressure conditions is 22.4 liters per mole. So if we look at it, something like a thermal decomposition of potassium chlorate over manganese oxide as a catalyst, we find that this produces oxygen gas as a product. So 2 moles of KClO3 as a solid can be heated with manganese dioxide as a catalyst to produce potassium chloride as a solid product and oxygen gas as a gaseous product, where we have 2 moles of potassium chloride to 3 moles of oxygen. So 2 moles of potassium chlorate form 2 moles of potassium chloride and 3 moles of oxygen. We can use molar masses to determine the quantity of potassium chlorate reacted, 2 times 122.6. The quantity of potassium chloride produced, 2 times 74.6. But then when we look at the oxygen, we find that we generally don't measure our gas products in terms of their masses, but rather of the volume of gas produced. So how many standard volumes of gas are produced from the reaction? In this case, 3 moles of gas would produce 3 times the standard molar volume of a gas at 22.4 liters. Gas products are usually measured in terms of their volumes then, rather than their masses. We can talk in terms of gas volumes instead of gas mass. For instance, 3 volumes of oxygen are produced in this reaction. And when we talk about volumes of gas, it can be any measure of volume as long as it's consistent. We can measure a amount of gas at STP in terms of a mole of oxygen, for instance. We can measure 22.4 liters. We can look at gas in terms of milliliters. We can look at gas at any particular unit of measurement as long as it stays consistent throughout the reaction for the same temperature pressure conditions and the same unit of measurement. When we look at gas stoichiometry then, generally gas is produced in an unknown amount because it's difficult to quantify the gas. We have difficulty measuring the amount of mass or moles of a gas directly because it can't be isolated into a single weighable amount in most cases unless it's contained within a vessel that's pre-weighed. The ideal gas law allows us to relate moles of gas to its properties. If we look at the ideal gas law, PV equals nRT. Dividing PV by RT allows us to isolate the number of moles, N. We can measure the other 3 properties, the pressure, the volume, and the temperature of a gas, and use that to determine the number of moles. So for our same reaction, our potassium chlorate decomposition, if we have 1.8 grams of a mixture of potassium chlorate and potassium chloride, so we have some product in the reaction mixture already. If this is heated until all of the potassium chlorate decomposed and 405 milliliters of oxygen are produced, which at 25 degrees Celsius had a pressure of 745 torr when it's collected, how many moles of oxygen were produced? And what percentage of the mixture initially was potassium chlorate? Using this same setup, we can calculate the moles of oxygen based upon the properties. We know that there are 0.405 liters and 405 milliliters. Converting from 25 degrees Celsius to Kelvin gives us 298 Kelvin, and from torr to atmospheres is 0.9803 atmospheres. We can plug this into our ideal gas equation, solving for N, so that 0.9803 atmospheres times 0.405 liters divided by the ideal gas constant times 298 Kelvin gives us 1.62 times 10 to the negative 2 moles of oxygen produced. So given the same setup then, at 1.62 times 10 to the minus 2 moles of oxygen, we can convert from oxygen into grams of potassium chlorate by multiplying by the stoichiometric ratio of 2 moles of potassium chlorate to 3 moles of oxygen, then by the molar mass of potassium chlorate at 122.6 grams per mole, yielding 1.32 grams of potassium chlorate decomposed to form 1.62 times 10 to the minus 2 moles of oxygen. If we compare this to the initial part of the mixture that we had, as expressed as a percentage, we find that we have 73.3% of the mixture as potassium chlorate. We produce 0.0162 moles of oxygen, and the mixture contained 73.3% potassium chlorate. Once we calculate moles of a gas, stoichiometry proceeds just like it does any other time. In the same way that we had our theoretical stoichiometry, which was without any sort of solution or gas product, then when we looked at aqueous stoichiometry, where we were measuring volumes and molarities in order to calculate moles and proceed from moles, here all we're doing is taking the variables of the gas state and using those to calculate the number of moles, and then once we have moles in hand, we can continue with the stoichiometry like we would in any other situation. Now, one specific caveat of gas stoichiometry is we have what's called Gay-Lussac's law of combining volumes. So according to this law, for the same temperature and pressure conditions, gas volumes are additive. If I had, for example, a reaction of hydrogen and chlorine, 1 mole of hydrogen plus 1 mole of chlorine forms 2 moles of hydrogen chloride. The volumes of those would be additive. So if I had half of a liter of hydrogen chloride, or sorry, half of a liter of chlorine and half of a liter of hydrogen, I would produce a whole liter of hydrogen chloride. I can measure volumes as stoichiometric ratios times whatever unit I'm measuring in. Half of a liter, a whole liter, 2 liters, 3 liters, molar volume of a gas at 22.4 liters, whatever units I pick as long as I'm consistent. Now, one thing that's particularly important about using gas measurements is we are able to calculate empirical and molecular formulas from decomposition of a gas. If we look at elemental analysis, we can calculate an empirical formula like we always have been able to. However, in order to convert from an empirical formula to a molecular formula, we need to know the molar mass of the gas. A gas product can be measured via the gas parameters, pressure, temperature, volume, but we can also get moles out of those measurements via the ideal gas law. So if I know the mass of a gas that I began with, I can calculate the molar mass of that gas once I know the number of moles involved. So for example, if I have a gaseous compound that weighs 0.345 grams and is 120 milliliters at 100 degrees Celsius and 1 atmosphere of pressure, and this gaseous compound is comprised of 54.5% carbon, 9.1% hydrogen, and 36.4% oxygen, what is its molecular formula? We can calculate the molar mass by converting all of our initial variable units into the proper units for the ideal gas law. Pressure is already at 1 atmosphere, volume is converted from 120 milliliters to 0.12 liters, and temperature from 100 degrees Celsius to 373 Kelvin. Plugging this into our ideal gas law then, solved for moles, 1 atmosphere times 0.12 liters divided by the ideal gas constant times 373 Kelvin yields 3.92 times 10 to the negative 3 moles of the gas. If I take the mass of the gas, 0.345 grams, and divide it by the number of moles in the mixture, then I have 3.92 times 10 to the minus 3 moles of the gas into 0.345 grams, yielding 88.04 grams per mole as the molar mass. Now that I know the molar mass, I can use the percentages to calculate an empirical formula by determining how many moles are in the percent carbon if we express this sample as being 100 grams. So 54.5% carbon becomes 54.5 grams, 9.1% hydrogen becomes 9.1 grams, and so on for oxygen. If I calculate them using their molar masses, I wind up with 4.54 moles for carbon, 9.01 moles for hydrogen, and 2.28 moles for oxygen. Dividing them by the smallest number, 2.28, I get ratios of 1.99 to 3.95 to 1.00, which are 2 to 4 to 1. This yields an empirical formula of C2H4O. The molar mass of the empirical formula then, 12.01 AMUs times 2 plus 1.01 AMU times 4 plus 16 AMU times 1 is 44.06 grams per mole. We know the molar mass from our previous calculation to be 88.04 grams per mole. So if we divide the molar mass by the mass of the empirical formula, we get 1.998, or approximately 2, as the value of n, where here in this case, n is the multiplier for the empirical formula, not number of moles. The molecular formula then is 2 times the empirical formula at C48H8O, 2. So we can use this process to determine the empirical formula of a substance if we can convert it into a gas state and measure its properties.